Good. All right.
Welcome, everybody. So today we have a guest lecture from Myles Borins. He works at Google, and he also is part of the Node.js project. So you're on the technical steering committee, right?
Mm-hmm.
Yep. And he's in charge of helping do Node.js releases, build quality security stuff, a whole bunch of stuff. That's probably not even mentioning all of it. All kinds of things. I remember we were at a conference one time, and we were at dinner, and you were in the middle of doing a Node.js release at dinner. So it was like watching the build happen, and he was like, okay, the binaries are going to go out, and then bam, there was a new version out. That was at NodeConf EU.
Yeah, that was like, was that last year or 2 years ago?
Probably 2 years ago, yeah. But anyway, so he's part of that. And I think you also are, so he's also on TC39, which is the technical steering committee for the JavaScript language specification. Cool. Did I miss anything you want to mention? Oh yeah, he's also a Stanford alum. So he was part of CARMA, the Center for Music, what is it?
Computer Research in Music and Acoustics.
Yes, that. And you're a musician.
Yeah.
Like so many of our speakers this quarter.
And I took CS 107 and Tharos was my TA, which is super fun.
Yeah, it was like 2012 or something, 2014? Yeah. Anyway, cool. Without further ado, take it away.
Yeah. Cool. Well, hi, everyone. Thanks for being in the class you paid for today. My name is Myles, and we're going to talk about security in the Node.js project today. I have a bunch of slides to kind of go through to like make some topics, although just talking to Ferris before class, I came up with like 3 more things that we could talk about. And then like we can open things to questions afterwards as well. So anything from just kind of like, open source to security to like working in the industry, like happy to answer any questions after we kind of get through the content we have here. That's me. If you've seen that face on Twitter at all, that's me. Sorry if you saw my tweets. I work for Google. I'm a developer advocate for Google Cloud Platform. Do a lot of work on the JavaScript ecosystem and also on GCP. Opinions expressed in this talk are solely my own. I've never seen this, I've never been challenged on this, but I'm not talking what Google cares about security right now. But if you haven't heard of what a developer advocate is before, it's kind of like an intersection of engineering, product management, a bit of marketing sprinkled in, a bit of kind of everything else. The super naive way I love to describe it is I help Google get out of their own way when making products. So I do work in cloud on a lot of our serverless runtimes, and we have great engineers. Some of them have been at Google since they graduated from school and have never really worked in the real world. Node is not a platform that we support internally at Google for some security reasons. Some I agree with, some I disagree with. But the engineers who are building our products don't necessarily know how the language communities expect things to work or how they should be working. So just because something is engineered correctly doesn't mean it's engineered the way people expect it. So as an advocate, a lot of my role is sitting in these meetings with various product teams and helping to advise them on making technical decisions, making decisions around release cadence. We'll get down and dirty into the code base when things are broken. So this actually can happen with security audits. There's a couple different products at Google that use Node, or stuff like Envoy, which is part of the Kubernetes ecosystem, has it embedded. And when internal teams find vulnerabilities, I'll often help with kind of escalating that and helping making sure that they're going through on releases. There's a lot of different avenues that I can end up working on there. But enough about myself. I made a bit of a glossary to start today to just go through some of the things we'll talk about. The first is MITRE. Does anyone know about MITRE by any chance? MITRE is an organization that does a number of different things, but the biggest thing that they do that people know them for is the CVEs and CWEs. So CWE is the common weakness enumeration. If you ever wanted to go and just, I don't have the internets. Let's fix this. I thought I did. Sorry, bear with me for 1 second, y'all. Get this on the stream too.
I can chop it out, don't worry.
Yeah, I'll just tether. It's taking too long. I think you'll like the name of my network. Oh, come on. Really? Do I have no service down here? I don't have service down here. Ferris, could you help me with this for a second? Because this will be, I checked everything but that. So Stanford visitor.
Just try going to example.com so that it'll intercept.
you have like custom
Oh, I
formats or
know
something?
what we need to do. So speaking of security, there we
Okay,
go.
there you go. Okay, cool. Oh, you were forcing it to HTTPS?
Well, we have like all sorts of plugins on the browser.
Got it. Okay.
Okay, there we go. So CWE is the common weakness enumeration. So like if you've ever wanted to like just see like a massive long list of all of the types of vulnerabilities that there could be, CWE is a list. We could go and search by like research concepts, development concepts, or architectural concepts. So we go and click here. We can see there's 1,000 type incorrect calculation, improper interaction, and then like we can click on this and it can go in depth and explains a little bit more about like what CWE 435 improper interaction between multiply correct behaving entities means. This is like for me really interesting because it's a common language that we end up having as researchers, and it helps like when you're reporting something, you're able to say like, hey, this is the CWE that I think is happening. And that brings us to a CVE, which is a common vulnerability and exposures. And so this is another program by MITRE, and the CVE is lists of found CWEs in projects. So you can go and look at the CVE list, and if we typed in, for example, here like Node.js and search, there's like far more than you'd maybe want to see. But the thing that becomes really cool with CVEs is, and let me see if I can find one that's a little newer. So here's one from a package, which is like a common injection in the PS package versions less than 1 for Node.js allowed arbitrary commands to be executed when the attacker controls the PID. They have a disclaimer about it. They have the HackerOne report. We'll talk about HackerOne in a minute. You can click through and we can learn more on this site, which is not loading, and we'll deal with that later. But you can kind of follow through on all of the different things going on here to kind of figure out like what is the attack that we're dealing with. And this database can actually be used as well if you're an operations team to kind of scan everything that you have in production, compare the version numbers, and you can know from this database like, oh, do we have anything in production that's vulnerable? And then we can cross-reference that against the CWEs and we can figure out how bad is that? Because depending on the environment that you're running, you create a threat model of that environment. Certain things are going to be higher severity than others. And we'll talk about threat modeling in a bit. CNA is a CVE numbering authority. So those numbers that we saw, those CVE numbers, are assigned by a CNA. MITRE itself acts as a CNA, and most vulnerabilities that are reported usually get their numbers from MITRE. The Node project used MITRE as our CNA for a very long time. But in 2017, a group of people on the security team decided, hey, it's a lot of work going through MITRE. It can slow down our release process. We don't want to have unpatched vulnerabilities, and we don't want to like be waiting for a number from MITRE to keep a 0-day unpatched. So we actually went through the work of becoming our own CNA. So the Node.js project is a CNA, and every year we get a block of numbers that we can assign ourselves. So we can actually assign those numbers to vulnerabilities before we've reported them to MITRE to be added to the database. And essentially, like when we put out our security releases, we can say, hey, here's the CVE number that it will be. We give the information to MITRE and they'll update it later. So it might take time to end up in various international databases, but we're not blocked by MITRE on getting fixes out. CVSS is the common vulnerability scoring system. There's a calculator that you can use that's a lot of fun. So let's say that you think you have found a vulnerability in some software. Well, like, is it a low-risk vulnerability? Is it a high-risk vulnerability? This calculator helps you figure it out. And when we talk about CVEs, and CWEs and CVSS, these are all interconnected. So if you find a vulnerability, that vulnerability will be assigned a CVE. That CVE will have a CWE for like what the actual vulnerability is, and then it will have a score based on this. And so we can take a really quick look at the base scores. So it's like, what's the attack vector? Is it network, adjacent network, local, or physical? And as you can imagine, something with a physical attack surface is going to be lower risk than something that can be done over the network. I'm going to try to make a really high risk vulnerability here, and we'll play it by ear from there. Attack complexity is another angle. Is it a really, really simple attack to do? Like, can I literally just send you like the word pi and your machine explodes? Like that would be like low complex. A high complex vulnerability may require, like the one that we were just looking at said, hey, you need access to the PID already. So like, is it an escalating attack that requires a lot of work? Let's just say that we have one that's really low. Privilege required, no, low, or high. Like how much system resource privileges do you need to do it? None. User interaction. Does the user need to do anything for this to happen or not? Scope. Does this change the scope of the actual system? So like after this vulnerability, have you escalated privileges? Let's say the scope changed. Confidentiality impact. So like, is there access to data that shouldn't be exposed? We're going to say, oh yeah, like we're getting your whole hard drive off this. Integrity impact. Does it have the possibility of affecting that data? This is a really important thing. Maybe we'll have time later to talk about side channel attacks. But side channel attacks for exfiltration is a really great example of something that has a very high confidentiality impact and that you can exfiltrate all sorts of data, but a very low integrity impact because it's not going to affect the integrity of that data. But let's screw the data on this system anyways. And then availability impact. So this would be something like a DOS. Will your attack be able to affect the availability of the machine? And let's say high. This is a 10 out of 10. Extremely high score. They have other things that we can go into, including temporal score metrics and environmental score metrics. For the sake of time, we won't go through them. But something that like I find is like just like a fun exercise, especially when I started going through this, is go through and just look at a couple CVEs. If you're interested in learning about like the weird ways that people hack systems, it is literally the documentation of every publicly available hack. Go look at the CWEs. If you want to learn all the different ways that you could attack a system, that's a list of them. And like if you think that you have a vulnerability, put it through this calculator, figure out like, is it actually as big of a deal as you think it is? And it turns out like what's interesting is you may not consider it, but like let's say there's no integrity, no confidentiality, high availability chains, unchanged network, low complexity, no changes to privilege, and user interaction required. So like this would essentially just be like a DOS that requires user interaction, and it's still like a 6.5. So like the metrics that they have here and how it's scored, there's an algorithm for it. But it's also meant as kind of like a fairly general threat model where they're coming up with these scores. So just because something scores really high on this system doesn't mean that for your system that you're doing the threat analysis on, that it is as high of a risk. Just something to think about. So I mentioned the term 0 day. 0 day is a vulnerability that has not yet been patched, arguably has not yet been disclosed. So it is out there, it is in the wild, and it can be taken advantage of. 0 days are dangerous because we don't know that they even need to be patched. White hat security researchers will discover 0 days and report them to projects. And at the point that they're reported is kind of like where the countdown is coming to disclosure and the countdown is coming to it becoming publicly available. One of the challenges of being a project like Node.js is we are a volunteer-run organization. So even our security team, our technical security team, no one is paid directly by the project or the OpenJS Foundation for the work that they do on the Node.js project. A bunch of folks like myself are lucky enough to work in positions at companies where they're afforded chunks of time to work on the project. So I get between a quarter and 3/4 of my time every week to work on kind of open source ecosystem related stuff, of which Node is part of it. But everyone who's working on the project is a volunteer. Our security team is also volunteers, everyone who's managing all of the reports and the people who are patching the vulnerabilities themselves. This introduces a couple interesting, you could call them risks. I don't know if it's the best way to frame it, but like one, we need to like significantly vet all of the people who are coming in before they can be given access to this information. It really helps when someone works for like a Google or a Microsoft or a large company, not necessarily because the company gives them like a resume line. It's more that like we know they can get fired if they screw with our stuff. So like that kind of bondability makes escalating trust easier. Also, if they have coworkers who can vouch for them, that helps a lot. But we do have vulnerabilities that have been reported to us that are still unpatched either due to the complexity or due to the lack of resources in particular subsystems of Node, that remain undisclosed but unpatched. And there is the risk of zero-day attacks being disclosed by security researchers if the project itself cannot patch it in a reasonable amount of time. A vulnerability, which we may have time to talk about later, called the hashwick vulnerability, was a hash seed vulnerability where a timing attack against a Node.js server could be used to determine the hash seed that's being used for randomization on the server. But because V8 was baking that hash seed into Node, it could also be used to determine what version of Node the project was using. So you could use something like that to do like a whole bunch of really weird DOSes. You could use knowing the hash seed to cause a hash lookup vulnerability where you just throw everything into, you keep making requests that would cause the exact same key into a lookup table, which just causes a server to run super slow. V8 fixed it, but it got disclosed before it could be fixed because V8 needed to completely re-implement the way in which they were doing hashing and the kind of hashing that they were doing, and that was a non-trivial change, and part of it still remains unpatched today.
People might not know what V8 is.
Oh, V8 is the JavaScript engine that's embedded in Node. It's also the JavaScript engine that's inside of the Chrome browser. So when you think about Node's architecture, we are a JavaScript runtime. How many people are familiar with Node.js? Okay, so Node.js is a server-side runtime. You can write JavaScript code and execute it inside of Node. The big difference I would say between Node and other JavaScript runtimes is that we embed our own system interface called libuv. So if you think about the browser as a JavaScript runtime, you have JavaScript, which is V8 in Chrome, and then you have Blink, which is the renderer and all the additional APIs that are on top. So anything that isn't just a language feature, so this would be network access or file system access, anything that would be essentially eventually binding to a Unix API, all of those are heavily sandboxed in the browser land. Node implements a whole series of system APIs that are of our own design or not standardized other than via implementation. So we run into a lot of these really interesting edge cases with the way in which we give programs system access. And when I'm talking about the use of V8 here is when you write code in JavaScript and hand it to Node, V8 is the engine that is executing that in a virtual machine. And then we have bindings into V8 that we create manually to give V8 system access. The JavaScript language itself, as specified by TC39, doesn't have any system interfaces. There is some work being done to create kind of a standardized system interface that could be used by JavaScript runtimes in the WASM community called WASI. And if we have some time, I'll dig into that after, but it's a little forward-thinking and tangential. Embargo is a really important term in all of this. Confidential information is embargoed. I am on the Node.js security triage team. Everything that is sent to us is under embargo until it's publicly disclosed. And I wear a lot of different hats, and this can make these kinds of embargoes a challenge. So I wear a hat as a Node.js release engineer. I wear a hat as a Node.js security triage member. I wear a hat as a Google employee in cloud working with our runtime teams on our runtimes. This embargo, when we have embargoes in Node, scopes to my work within Node. So it would actually be against the rules of our project and arguably illegal, although I'm not going to try to lawyer cat that, but I can't disclose the embargoed vulnerabilities to my peers at Google before they are publicly disclosed based on our current embargo policy. And we've actually had problems with this in the past where members of our security team leaked embargoed information to their companies, which arguably gives them competitive advantage over other vendors. We have discussed as a team trying to create an early access embargo program for people who run Node.js runtimes. So for example, whether it's AWS or Microsoft or Google, with independent of what cloud vendor I work for, I want people who are running Node to have a secure environment to run their code. I would love us to have an early embargo program so we can bring in these runtimes so they can patch and test and ensure that these security vulnerabilities are patched so the time between 0-day and everything being patched in production can be as low as possible. But unfortunately, the politics behind this and even just like the technical ability to implement these makes it difficult. So as it is today in Node, everything that happens security-wise is embargoed and embargoed to the project. And if I were to talk to my employer about any of the things that are disclosed to me, I could be removed from my position working on these things. And people take it really seriously. And one of the last ones I'll talk about here is triaging. I used the word triage before. Triaging is a process that we do when vulnerabilities get reported to the project. And we do that through a thing called HackerOne. And I'll show you HackerOne in a bit. Has anyone used HackerOne before? HackerOne is a website that you can go to, and various projects have landing pages on there. And so you can go to HackerOne/Node.js, and if you have found a vulnerability in Node.js core, you can report it through HackerOne. HackerOne then acts as a management system for those vulnerabilities. They allow you to put your CVSS score in there. They allow you to put your CWEs in there. They allow you to keep track of how quickly we are responding, and they actually give us a score based on a project as how quickly we do things. HackerOne actually donates resources to the Node project to help with managing these things. So when new reports come in, we actually have the HackerOne team review these reports first and pre-triage before handing off to our team to ensure that our time is not being wasted by reports that are not really a problem. This has bit us before. It's kind of like touch and go. The researchers are good, but they don't know the platform super well, so we've had things kind of get mischaracterized before. We also run a HackerOne for the ecosystem, so if you find a vulnerability in a project like Express or torrent stream or any of the various modules that are in the ecosystem, we have a separate team that manages triage of those. And so stuff comes into HackerOne, and we'll get a little bit more into kind of the life cycle of a vulnerability in a minute. And the last one I wanted to mention is the IBB, which is the Internet Bug Bounty. The Internet Bug Bounty is a really cool program that's run by HackerOne, and it's a fund of money that's used to pay bug bounties to security researchers who find bugs in what's considered core infrastructure of the internet. So a lot of projects run bug bounties, and HackerOne actually also acts as a way to pay out these bounties and record the bounties and have like hacker reputation. So these different projects that you can see here, OpenSSL, Nginx, Apache, Perl, PHP, I guess the internet, all of these projects participate in the IBB, and the IBB is this large fund that will pay out bounties for open source projects, generally scoped to remote code execution is primarily what they're for. So Node participates in the IBB program. I am proud to say that we have not paid anyone out yet, not because I care about the money, I just don't want us to have our CEs in Node. But it's a really, really cool program. We have discussed about making kind of above and beyond program within Node Core itself so we can be giving some degrees of bounties to security researchers. But there is kind of like a high level question here with bounties about like whether or not they create the right incentives, and especially for a volunteer organization like ours, if we make too many bounties, and you know there's people who can make a whole career off of bug bounties, like if we have the resources to really manage the kind of traffic that could come in with them. But so we're going to talk about a couple different types of vulnerabilities today. I've mostly been focusing on the first one, and we will primarily focus on this, which are vulnerabilities to the core Node.js platform. So Node itself is a software project. It's built of a whole bunch of different parts. And if there is a vulnerability in Node itself, that means every single application on the internet that is running on Node is vulnerable. So that's bad. We don't want that to happen. But there's also vulnerabilities in the Node.js ecosystem itself. You know, there's a massive package ecosystem in NPM of, I think, like 1 billion packages or something silly like that at this point. And a lot of those packages can have vulnerabilities in them, and there's a lot of different vectors. And if you're building applications, you need to worry about the infrastructure you're built on top of, not just the platform. And finally, also vulnerabilities in your applications themselves. Now, arguably, these second two can become kind of conflated because the packages that you use from the ecosystem in your application are part of your application, but I do think that they are distinct to think about from a threat model perspective and when you're thinking about kind of how do we avoid these bad scenarios. So in Node.js Core, there's a couple of different kinds of threats. This is not all of the threats, but some of the threats I've seen us try to worry about. Buffer overflow attacks, denial of service attacks, data exfiltration, remote code execution, hostname spoofing, and vulnerabilities and dependencies as well. So it's not just the ecosystem that needs to worry about dependencies. Node has a deps folder, and we have a bunch of stuff in there, including ICU and V8, libuv, zlib, NGHTTP2. We have a whole bunch of C++ code and other dependencies that are embedded in Node itself. And if we ship that code, and that code's vulnerable, well, then Node's vulnerable. And a non-trivial number of the security releases we've done over the last 2 years have actually been patching OpenSSL because people love to hack OpenSSL, and we want HTTPS to be reliable. So I mentioned the life cycle of a vulnerability. So let's dig into that a little bit. So you're a researcher, and you've figured out that you have a bug, and you report that bug through HackerOne. So it gets triaged through HackerOne. It ends up in my inbox, and maybe I don't look at it in the morning because I'm in a meeting, but hopefully someone looks at it. And eventually we communicate with the author. If we need more information, we'll ask for more information. We'll go back and forth. But eventually, if it can be confirmed as an actual vulnerability, then it is considered triaged and being worked on. It's also possible that it stops at this point. We had a vulnerability reported yesterday, for example, that was neither a vulnerability nor a problem with Node. It was a really weird way that if you define things with let, that like variables are not able to be used. But it's arguably a spec bug, but it definitely wasn't a security problem. But we triage that, we respond to the person, point them at the right information, and then like say, hey, that's not a real bug. And then I think as far as HackerOne is concerned, you actually have like a hacker reputation. So if you file things that are not bugs like that, you get like -5 to your score. If you get like a bug that's actually triaged, you get like +7. So like you can get reputation because points. We then work on identifying a solution, and the hope would be that this is something that we can do rather quickly. But as I mentioned with that hash seed vulnerability, sometimes this can take months. Sometimes like part of this is sitting in triage for over a year. That's very, very rare. And in fact, the hash seed vulnerability is the only one that's really been in that case. But we do try to do this as quickly as possible. And we generally try to stay in touch with people generally on like a weekly basis, but if possible, like every 24 or 48 hours, especially if they're really, really high severity vulnerabilities. We create a security release. This part is the most painful part of the whole process. As I mentioned, Node is a volunteer organization. Another part of our organization, which is all run by volunteers, is our build team. So our CI infrastructure, which is absolutely ridiculous. Oh, come on. This is killing me. So this is our CI. It is a janky Jenkins with so many different workers. So like one of the things with Node that's particularly interesting is we have so many different platforms that we support. So it's like every flavor of Linux that you can imagine, including like BSD, as well as Solaris. We also support multiple builds of Windows, multiple builds of OS X, a whole bunch of different ARM systems. We do Z system. We also do multiple PowerPC and I think S390. So there's all these different architectures that we support. So you can see like all of these are like different build bots that we have, some of which I guess are red. Some of them are containers, and we test in a whole bunch of different container things, including like Alpine. And actually I'm going to take a note because we can get back to this one later, but there's weird vulnerabilities that can come just from system differences. There was one that I ended up having to patch a couple years ago where what is it? It's like the symbolic link APIs, like when you're determining like cycles and symbolic links. RealPath is all implemented in JavaScript in Node because in 2008, around the time that Node was originally being written, there was a buffer overflow attack in the RealPath implementation in Unix that was used to do remote code execution via FTP servers. So instead of binding to RealPath 3, they just implemented RealPath inside of Node proper. And when we eventually tried to fix that in Node by binding against RealPath 3, it broke a whole bunch of stuff in the ecosystem, because the order that you would get system errors, whether it would be a RealPath error or a MITRE error, was totally dependent on the system. So we broke a module called glob and only broke it on like Darwin and BSD because of just like platform inconsistencies in the implementation of the Unix APIs. And we had to do like a really weird patch to make sure that if somehow someone was running Node on like an old version of Unix that had that vulnerability from 2008, my super naive hack there was like literally it just throws during compilation, so you could never compile it to work on one of those systems. And no one's complained, so I think we're good. But anyways, that was a tangent and a half. The reason I brought up the CI stuff was that our CI has all of these workers. These workers are extremely specific, and they are persistent. So it's not just like we're running something in a container. If any of you use something like Travis, for example, your CI is running in a container, and then when your process is done, that container's killed, so you don't have to worry about things living on between runs. Because we have all of these systems, and because to a certain extent, but not totally, our CI is public-ish, at least to like collaborators, but I believe you can click through and get access as long as you authenticate with GitHub. You can kind of go through and look at any of the things that we're running. You could look at the output from the console from any of the things that have been run. So if our CI was still public when we're testing the patches for our security vulnerabilities, someone could go through and look at the system and just through like the commit name, maybe like figure out what 0 days we're trying to patch. So when we actually get to testing against all of the different platforms, we need to shut down our entire CI for all collaborators except for the triage team and the release team, which ends up being quite disruptive. But kind of like I went through that whole thing to talk about like when we talk about doing a security release, this isn't just like a thing that we could do at any time. We need to give the build team a heads up so the build team can go and lock down the infrastructure and make sure all the IAM roles are set up so that the access management doesn't allow other people in who shouldn't be in. We need to make sure that collaborators who have access are aware that like, hey, don't run anything on CI right now, because we don't want to have any problems. We need to make sure that collaborators know they're not going to have access to CI, so if you're planning to get work done, you won't be able to. And then separately from all of that, we have a whole other sandboxed CI just for doing releases that we need to make sure is wired up to get things from embargoed repos, because we won't even be working on the main repo. We may be working in different forks, and so we need to make sure that our CI is all wired up to have access to all these things. It's a pain. But once all of that is done, we can then finally disclose the vulnerability itself, issue a CVE score, publish a blog post. We post on a message board about the security vulnerability itself. And then often what will happen also with this is people around the internet start updating their stuff or not. So for a little bit more information on our security process, you can go to nodejs.org and click on the security tab, which kind of has a lot of what I've discussed documented. It tells you, like if you have a bug to report to Node, you can click here to report through HackerOne. We'll acknowledge within 24 hours and give you an update within 48. And one of the things that's great about HackerOne is it actually tracks this and it gives us metrics. So if our security team is not keeping up with this SLA that we're offering, that's the service agreement. I forgot what the L stands for, I should know. Talks about our bounty program, and it also talks about reporting third-party bugs and about our general disclosure policy. And that was what I was talking about regarding things being embargoed and when they get disclosed. And if you want to have updates, we do have this Google group called Node.js It is a read-only list that every time there is a new security release, we post the update in here, as well as why we had to do the release. And I'm kind of happy that if you look here, you can actually see we've only done 3 security releases this year, which is far better. We had a lot more in 2018. So going back here, the next one I want to show you really quickly was the Node.js HackerOne. So if you were to report a vulnerability through HackerOne, this is what the landing page would look like. Has a little bit more information about the policy and a little bit more information about, hey, where do you go to report third party? You could see that our average time to resolution, like our our average time for first response is 1 day, average time to triage is 2 days, and we meet our response standards over the last 90 days 92% of the time, which is pretty good for a team of less than 20 volunteers. You could see that we have this program bounty with a minimum bounty of 500. We've paid no bounties because we haven't had any RCEs. But you can see that we've had 12 reports received in the last 90 days, with the last report resolved 3 months ago, with 10 reports resolved and 19 hackers thanked. You can, on any HackerOne page, look at the hacktivity, which will show you like what has happened. You can see most of these are embargoed, but some of them are available to be seen. This is one that is kind of fun. It was the registry.nodejs.org domain takeover. So this person found that there was an abandoned Node.js org subdomain called registry.nodejs.org that was pointing to Fastly. And Fastly doesn't require any proof of DNS ownership to register new distributions that use a given domain. So he did an effective takeover of registry.nodejs.org, which someone may decide to, like point a package manager at, which would be bad. But so we worked with them. We fixed the CNAMEs. We deleted the CNAME record and went through and did an audit of our entire DNS stuff there. But the reason I wanted to talk to you all about this, because a couple things. A, you would never think about this necessarily as a vulnerability to Node.js. It was not a software problem in the project. This was a domain entry on our website. But our project relies on that website being a canonical source of information. So this was, in my personal opinion, like an attack vector to the Node.js project. And this is when I talk about the idea of like threat modeling, like this is the kind of thing that you need to take into account. Like what are all the different ways that people can attack your project or take advantage of people who are relying on the services or products in which you're offering? If someone put something on registry.com and then tweeted about it or posted it, like they could have hacked a few people and gotten some important information before we could have reacted or known anything. Thankfully, Dade was a good actor and reported this to us, but like they had arguably taken over a portion of the Node.js domain and could have done some pretty nasty stuff with it. So if you wanted to submit a report, you would click Submit Report, and then it will take you through a login flow. I'm not going to log in, because if I logged in, then you're going to see a whole bunch of stuff which you shouldn't see. But if it is something you're interested in, if you're doing security research, it's a really great way to kind of like build a bit of a profile for yourself, maybe make some extra cash on the side, but also just similar to like going through the CVE databases, all the vulnerabilities that have been reported on HackerOne that have been disclosed are able to be gone through, and you can kind of look at the history of the conversation that's happening there. So I selected a couple of my favorite vulnerabilities from the last 2 years and thought that we could go through them really quickly. So this is CVE 2017-14919, which was an improper input validation. So if we click through to the CVE itself, we could see Node.js before 4.8.6, 6.x before 6.11.5, and 8.x before 8.8 allowed remote attackers to cause a denial of service, uncaught exception, and crash by leveraging a change in the zlib module 1.2.9, making 8 an invalid value for window bits parameter. It's a bit of a mouthful. If we look here, we can see it's CWE20, improper input validation. We can click through and see what that CWE is, and it talks about all the research concepts that it's relevant to, an extended description. You could kind of go through here to see like all sorts of examples and whatnot, in places where it's referenced in standards. But let's go back here and we can look at the blog post and maybe get a little bit more information. So we could see here. Yeah, here it is. Node.js was susceptible to a remote DOS attack due to a change that came in as part of the zlib 1.2.9 update, which, by the way, was a security update to zlib. So upgrading a dependency that we had to patch a security vulnerability introduced this DOS into Node. 8 became an invalid value for window bits parameter in the Node.js zlib module, which would crash an exception when you were trying to create a raw deflate stream, which Node was doing internally. 8 was a valid value to pass to create deflate raw, prior to this update, which just kind of hooks into zlib itself. And this should have been, in my personal opinion, a semver major change to the interface of zlib, but they didn't. They did it as a semver patch, which surprised us. But WindowBits 8 worked before, and inside of zlib, what they would do is if you passed WindowBits 8, they would just replace WindowBits 9. And it's because they don't actually have the way to encode an 8-bit window deflate stream implemented in zlib at all. I have a pull request that I sent that hopefully would fix that. It never got a response, so that's kind of where we are. But what would end up happening here was that if you had code that was setting the window bit manually that would work on the versions of Node prior to this patch, it would cause Node to crash because zlib threw an exception when you passed 8 as a window bits argument there. So if you had some sort of way to send something, like let's say you had a zlib service and allowed people to pick the window size, they could create a denial of service attack and hurt availability of your service. So show you really quickly what the fix looked like, because it's super naive and fun. Maybe it will eventually load. Come on.
Do you have to read off the visitor network? Hope not.
Oh, there we go. Okay, so I wrote this patch that has a little bit more information in the commit here. On April 4th, 2017, Node.js versions 4.8.2 and 6.10.2 were released. These versions bumped the vendor zlib library from 1.2.8 to 1.2.11 in response to what it describes as low-severity CVEs. In zlib 1.2.9, a change was made that caused an error to be raised when a raw deflate stream is initialized with window bits set to 8. In zlib 1.2.9, 8 became an invalid value for this parameter, and Node zlib module will crash if you call this. On some versions, this crashes Node and you cannot recover from it, while in some versions it throws an exception. The per message deflate library up to version 0.1.5 does make a call with Node try catch. So if you are using that library inside of your package, that would just cause your service to all of a sudden become unavailable once you updated. This commit reverts to the original behavior of zlib by gracefully change window bits 8 to window bits 9 in a raw deflate stream. So you could see, we document all of this in zlib itself, and then this is the fix. And we also have a test that we removed, which was confirming that indeed worked, and then a new test that was added to ensure that we would never regress here. And I think, if I do this really quickly, if we take a look at zlib GitHub, you could see my attempt to fix it, which brings in, like a little bit of an algorithm to allow 8-bit windows, but this has remained unreviewed and unlanded, so we need to, for now, keep that hack in Node, unfortunately. So that was a fun one. CVE 2018-7160 was authentication bypass spoofing and reliance on reverse DNS resolution for a security critical action. So this is a kind of fun one. Makes more sense when you read the actual vulnerability. The Node.js inspector in 6.x and later is vulnerable to the DNS rebinding attack, which could be exploited to perform remote code execution. An attack is possible from a malicious website open in a web browser on the same computer or on another computer with network access to computer running the Node.js process. A malicious website could use a DNS rebinding attack to trick the web browser to bypass same origin policy checks and allow HTTP connections to local host or to hosts on a local network. If a Node.js process with a debug port is active, is running on local host or on a host on a local network, the malicious website could connect to it as a debugger and get full code execution. So If you've ever used Node's Inspector API, you do node-inspect. That lets you connect to Node with the Chrome inspector. It's really great for debugging, but it turns out that like with this DNS rebinding attack, arbitrary websites could trick Node into thinking that it was running on localhost and execute things. So like let's say that you were running Node on your personal computer, testing an application or running a slide deck like I'm running right now, and happened to be debugging your application and had the debugger open, and then you were going through like the docs or something like that on the web, and then, oh, you forgot, and you looked at Twitter, and then you clicked a link. Like, if your service was running on your local system, your whole local machine could have gotten pwned by this attack. Similar attacks were a problem earlier where we listened on star instead of localhost, and we didn't do kind of like an isolation to just localhost, so that if you were running a system in the cloud that had the inspector exposed, anyone could have connected to it, not just something on the same origin. So these are just kind of small things that you may not think about. Like maybe you're throwing something up on a server of yours to debug, and you have the debug port exposed, which is like 5844. Well, there's probably bots just crawling across the net constantly looking for systems that have 5844 open. And if you don't have it set up to like lock down with some sort of credential or cookie, you could just have your system owned really quickly. If we look at the blog post for this one, so the attack was possible from malicious websites to open in a web browser on the same computer. The mitigation may affect some remote debugging scenarios. For example, it may no longer be possible to debug a remote computer by using a host name. Either connect using the IP address or using an SSH tunnel to work around this additional security request. This change is therefore a breaking change. However, as per the Node release plan, we're including it as a security fix on all impacted release lines as a semver minor rather than a semver major. How many people are familiar with semantic versioning? So when you see a software version that's like 8.10.1, the first digit is what's called a semver major, the second digit is what's known as a semver minor, and the third digit is a semver patch. And if you're using semantic versioning, which some projects like Node do and some projects like V8 don't, the version numbers actually have a semantic meaning. The semver major digit, which is the first digit, means breaking changes. So if you do anything that breaks any interfaces in the software, you are expected to increment that digit. The Node project, we do every 6 months a new semver major version. So we have a master release line that everything just lands on when it's done. Then we have different release channels. So we have a separate branch for every one of our major releases. So right now we have version 13, version 12, version 10, and version 8. So 4 versions that are being maintained. They're each their own independent branches. And when we cut new releases from each of those individual branches, we backport changes from master onto those specific release lines. But we do not backport any of the semver major changes to any of those release lines. The second digit, semver minor, refers to changes that are non-breaking but add new features. So if you add a new API or if you extend the capabilities of an API in a way that doesn't change behavior or expectations, you're expected to increment the semver minor number. So we just unflagged ECMAScript modules in Node 2 days ago. It will launch next week. The way in which we implement it does not change any software using the old CommonJS loader. So that will be considered a semver minor change because it is purely additive. Semver patch are changes that do not add anything and do not break anything. So these can be doc fixes, new tests. It can be fixes to bugs. It can be changes to experimental APIs that aren't part of our semver policy. Now, the thing that we mentioned here that's really important, though, is that we landed a breaking change as a semver minor. So this is part of our release policy that essentially we state anything that is a security update, something that we need to patch because it is making our platform insecure, can land as a semver minor even if it's breaking. So in the case of this API, we just like hard broke the ability to remote debug via DNS using the domain name directly and not the IP, which for cloud, this is a great example of something I may want to have like broken the embargo and told our teams because we have like remote debugging tools that are relying on these interfaces. We have products that are out that rely on this. But I could not tell my team until it was embargoed. But we broke it. We broke it hard, and we did not look back, because you need to do what you need to do to make sure that things are safe. A great example of something that's along the lines of that right now is Node has a legacy parser for HTTP. It's called HTTP_parser. It's written in C++, and it is a painful ball of C++ that no one really understands. Fedor and Dutney, who's like he was the one who came up with that hash vulnerability that I was talking about before. He's one of the most brilliant hackers I know on the planet. He wrote an LLVM compiler that can take TypeScript and compile it like directly to bitcode. So it doesn't even like transpile it to JS. It just like takes TypeScript and then turns it into a binary. And he rewrote the whole HTTP parser in TypeScript in a way that was completely like semantically equivalent, but like way easier to manage. And because it's written in TypeScript now, rather than C++, there's more people that can help manage it. In Node 12, I believe we switched the default to this new TypeScript parser, but Node 10 and Node 8 are still using the old HTTP parser. Now, we are pretty sure that they are semantically equivalent. We're pretty sure that switching from one to the other wouldn't change anything, but we can't know for sure. And all of Node's even releases are what we call LTS, long-term support. They get 3 years of support, but once they go into a long-term support stream, we do not make wide changes. So like even if they were semver minor or semver patch, there can be semver patch changes that change performance characteristics, such as refactoring for speed improvements. We don't land anything on these branches that could potentially change the performance, even just to make it better, because you don't know if you change something to make it faster, that in an extremely large system, it breaks things in unexpected ways that maybe have expectations based on timing. So we are not right now switching the old HTTP parser to the new HTTP parser in Node 8 and Node 10, which are both kind of in a maintenance period now, because we don't want to risk changing expectations, changing performance, or breaking anything. But we did make it extremely clear that there are a bunch of vulnerabilities that may be discovered in that parser, because we know that it has problems, and that if in the future vulnerabilities are disclosed, we may choose not to patch those vulnerabilities, but rather switch the default parser. And that would be arguably a semver major change that we would land in a semver minor. A lot of words. Thanks for bearing with me on that. But like these are the kind of things that we need to think about as a platform when we're releasing, when we offer stability, and kind of finding the balance between stability, reliability, security, and maintainability. And that last one, maintainability, is extremely important. Because as I said, like we are a bunch of volunteers. We do not have all the time in the world to work on all of these things. So we need to kind of be pragmatic and choose when we can and can't fix things, which is the exact reason, for example, when Node 8 goes end of life in December, like we won't patch it again, even if people find vulnerabilities. And we're actually end of lifing it early because the version of OpenSSL that it relies on is ending life before we were going to end of life that release line. So rather than keep a version of Node on a version of OpenSSL that doesn't have security support, we're just ending it 6 months early, which I'm more than happy for. It means less work. Okay, so one more CV that we'll go over, CV 2018-12115, out of bounds right. So this was an interesting one. In all versions of Node.js prior to that, when used with USC2 encoding recognized by Node.js under the name USC2, USC-2, UTF-16LE, and UTF-16LE, buffer write can be used to write outside of the bounds of a single buffer. Writes that start from the second to last position of the buffer will cause a miscalculation of the maximum length of the bytes to be written. This isn't good. This is an out-of-bound write. You don't know what's existing in that other memory. And out-of-bound writes could be used for all sorts of other escalations. And this is a thing that I learned over time that I found really interesting, is that like often an attacker won't just be using one attack. It's like, hey, when I take 3 or 4 different attacks that I know about and tie them together, then we can do something like really interesting. So like this out-of-bound attack could be used immediately as like a denial of service, or it could be used for something like a remote code execution. If you knew that the place where you're writing out of bounds is where a reference to a function that's going to be called is, you could potentially put a payload there. So that wasn't good. And then this is like a fun one if you just wanted one blog post to read through that's like going to get the best bang for your buck. November 2018 was a doozy of a release. So I told you about port 5858. So this was interesting. After we fixed it in the inspector protocol, we realized that our old legacy debugger actually had all of the same vulnerabilities as the new inspector-based debugger. So we had to go back to old versions of Node that were not patched because they didn't have the inspector and patch that. So like we actually created a 0-day. So this is like a cool thing. Like we patched the inspector and we stated, hey, this is a vulnerability and this is a way that it could be escalated. But we completely ignored our legacy debugger that had all of the exact same vulnerabilities. So an attacker totally could have gone and seen, oh, they like fixed the inspector. I wonder if the same attack works against the debugger, and then would be able to use that attack against older versions of Node and legacy things that were in production. We had a denial of service with large HTTP headers. So if you used a combination of many requests with maximum sized headers of 80 kilobytes per connection and carefully timed the rate that you were sending the headers, it was possible to cause the HTTP server to abort due to heap allocation failures. It was possible that if you had proxy layers in front of your service and you weren't just exposing your service directly, that it wouldn't have caused a problem. But like this was a really interesting bug because it was reliable and you could take down kind of like anything with the right timing. Slow Loris was another one that was somewhat similar, which was like a timeout of 40 seconds was applied to the HTTP headers because this kind of like slow request attack could be done, and it caused like a memory leak that if you made a request and it was a slow request and it kept the request open for a certain amount of time and that at a certain cadence you just kept them coming, you would slowly do resource leaks of the node process, and you could just essentially cause a process to start taking like orders of magnitude longer to process requests. And this one was like really, really nasty because there wasn't necessarily a good way for you to even tell that your system's performance was degrading over time. And if someone was doing this really slowly over time, they could just kind of like really, really slowly degrade your service and just like, you know, get it to the point where like, wow, nothing's working, and then you restart it and then it works again. And you're like, oh, okay, cool, and then just it happens again. So it's like one of those things, just like mess up your day in a way that would be really hard to know about. Hostname spoofing in the URL parser for the JavaScript protocol was another one that came out that day. There was an HTTP request splitting CVE that came out that day, and then a bunch of timing attacks against OpenSSL. So anyways, if you want to learn about like a whole bunch of them all at once, I suggest the November 2018 blog post. There's a lot of fun vulnerabilities in there. So we talked about threats to Node, but what about like to your application or to the ecosystem? What are some things that you may have to worry about there? Well, everything from before. Like you don't have to not worry about those. But you also now are susceptible to things like supply chain attacks. You're now susceptible to things like weak cryptography. And to be honest, I'm actually being kind of arrogant to pretend that supply chain attacks and weak cryptography can affect Node as well. But generally, this is something more of an ecosystem problem. This last one, though, I think is really important: poor developer experience. So Faris and I were talking a little bit earlier about like a transition I may be doing in my career right now towards Google's open source programs office. The programs office at Google is responsible for maintaining the policy for open source compliance at Google. And one of the things that we've been talking about is like the compliance process at Google to open source a library or to patch upstream could be considered by some to be a little bit too aggressive. If you want to make your own repo, you can go and check up Google patching. All of this stuff is online, but you have to go through like a whole launch process if you want to make a repo on GitHub. And there's a lot of people who don't agree with this policy or think it's too much work. And not me, but other people in response to this will just go and make their own repos. And this is why policy and process needs to be thought of in a way that is balanced with pragmatism and velocity. If you are a security researcher on a security team of a company and you make a really, really like robust and arguably like dogmatic process that it's hard for people to follow, They're not going to. They will find ways to skirt around it. People will value velocity over anything else. So creating a poor developer experience through trying to lock down your systems could actually make you less secure. One of the ways, and we'll talk about this in a bit, that I've heard like getting around this is like, keep development clusters that are isolated from everything else. Let your developers run whatever the hell they want on those developer clusters so that the iteration of actually like building the solution happens in a sandbox, and then do like a full review of all the dependencies before it promotes to production. Highlight the things that are inside of that dependency tree that they can't ship to production. And at this point now, you're not saying, hey, you can't use all these modules, try to figure out this from scratch. Now the problem that they have to solve is, like these really 3 or 4 specific APIs that I understand and know their capabilities need to be replaced. That's just one kind of pragmatic way of approaching this. But in general, like if you are in the position to help pick security policies and process for an organization, do keep in mind that people will ignore you if you make it too much work for them to deal with it. And that is arguably like the highest vulnerability that you'll have as an organization. And malicious third-party code is also a problem, and it's deeply tied to supply chain attacks. And query injections are another obvious place where you can get bit in applications. So I think we had sent out in the document to you all this NodeSec roadmap. Mike Samuel wrote this. He was a security researcher at Google. Google works on a giant monorepo, and he had been there since before the monorepo doing JavaScript, just to give you an idea of like how long this person had been doing JavaScript at Google. Some work that I had been doing internally is trying to get more internal adoption of Node.js for Google products, which was not entirely blessed, although there are some ways to get it into production now. Part of the process of doing that was a full review from our security team, and this artifact is one of the things that came out of this. If you are looking at creating, like a threat model, threat environment, and security process for a team that is building a Node.js application, I highly advise going through this document. It goes through, hey, like what is the threat environment that we're talking about? What's the difference between server and client-side code? What are the classes of threats that we have? What are their frequency? What are their severities, at least for the model that they've created? This is a really interesting thing to think about in creating a threat model, is that the severity for your threat model may be different. So at Google, we have a whole bunch of serverless runtimes. Have any of you heard of like Cloud Functions or Amazon Lambda before? Lambda and Cloud Functions allow you to just give like a single function that's written with a particular signature. We deploy it for you, we scale it for you. It's just expressed in a container, but whatever. But like, it's really great from like a velocity standpoint of being able to get things out really quickly, and great to not have to manage that infrastructure. But your security concerns become far different when you're running in that kind of environment. Like first of all, with Cloud Functions, we update the node runtime from underneath you. We also patch CVEs on the operating system from underneath you. So we'll redeploy your functions. Anytime, like the base container image that we use for Cloud Functions is based on Ubuntu, I believe right now. And there's a whole bunch of system libraries that come out of the box on there. If any of those have CVEs, or if Node does a new release, we patch that and release that for you. So like some of the stuff that we talked before about like making sure that you have the latest version of Node, well, like that's not really a threat model for you anymore. Another one that's not really a threat model there as much as DOS, or at least not in the same way. Cloud Functions run with one tenant per one function. At least that's the scaling model that we use at Google. So each Cloud Function will spin up a new instance of that Cloud Function for each request that comes in on the server. What this means is that if someone is trying to attack you with a denial of service, they will take down that one instance, but it does not affect availability at all for other people who are trying to connect to your service. Now what it can do, and this is a totally different kind of attack, is it could do a resource attack. You have a credit card attached to your account. You pay so much for every single function that it executes. If someone knows a DOS that can just like cause your Cloud Function to halt and just like not like run until the max length, they could scale up a whole bunch of traffic against your Cloud Function and then kind of like just drain the resources of your account and cause you to spend a whole bunch of money. Your system will always be available, but you'll waste a bunch of money. I mention this because this is a different threat vector. This is a different kind of thing you need to put in place to affect it. You can, in Cloud Functions, set like max scale. You can set different kind of observability warnings to see when your traffic spikes beyond a certain point. If you had a single VM that was running a node service, a DOS on there will look very different than a DOS in this other environment. But just in general, like this kind of threat modeling is really important when you're thinking about where you're putting your stuff, how it's running, how it's scaling, how tenancy is being managed, and how you have to worry about the availability of your service. So it goes through all of these different vectors. It talks about like dynamicism in Node, why it's really easy and why dynamicism can be a problem. It talks about like knowing your dependencies and that workflow that I had suggested, for example, of like, you know, working in a sandbox and kind of making it harder as you get to production with your dependencies comes directly out of this doc. It talks about potential solutions and incident reports and how to run scripts locally. That's another potential threat vector with Node. When you run npm install, there are post-install scripts that can run on every single module when you install them. So essentially, npm install is a remote code execution environment. It's doing that on purpose because you're saying, hey, do this. In fact, just running npm install is executing code on your system. But it all depends on where you want to like draw the line. So if you are deploying things to production, well, if you are running npm install and building your Docker container inside of a sandbox that's thrown away after you build your app, well, that's fine. But let's say you have a single living VM and you're running Docker in that VM and running npm install in a folder before Dockerizing the thing, and that's like directly on your VM and not in any sort of isolation, like you are risking compromising your main system. So these are just like, you know, things to keep in mind. And they get more into like solutions and sandboxing techniques in here. I won't dig too much more into this, but just like another document that's just like really great to dig into, has a lot of great information. And I would even argue just beyond Node, like think of it as a case study in Node, but like this kind of way of like threat modeling and coming up with a security policy and program is a great way of kind of clearly identifying what needs to happen to have secure applications in production. So the ecosystem on HackerOne, we'll look at this really quickly, but just another place where you can go through and see like a whole bunch of vulnerabilities, learn about like really weird stuff that's happened. Similar to the Node.js HackerOne that we were looking at before, you could see all of the vulnerabilities that have been disclosed, and there's a lot of them. I think there's over 180 of them. Some of them are really, really wild and weird, and like, I don't know. I'm always so impressed by the people whose brains work this way. Like I'm not the kind of person who's constantly thinking about how to break systems, but like, oh God, like they're so creative. Bauer, arbitrary file write through improper validation of symlinks while package extraction. So like that's not good. That's not something you want in your package manager. Let's see. Command injection in the ASCII art package. Let's look at that one really quickly. So this was a severity 8.6. It was a generic command injection. Images, fonts, tables, ANSI style, and compositing. And that's about the module and the stats. So it's not super huge. It's only like 1,400 downloads a month, so that's better. But it does not sanitize the target command line argument and subsequently passes it to the child process exec. So that's not good. But yeah, like another place where you can go through and see like a lot of practical hacking and how it was done. And now with knowing the language of CWE and CVE and MITRE, you'll maybe have a little bit of an idea of how to go through. And if they mention on here, for example, like let's look at another type ORM, here's a SQL injection attack. Well, you could see, hey, well, the weakness here is SQL injection. So you know, like you can look up Google CWE SQL injection and see, hey, the history of SQL injection, what qualifies as SQL injection, what doesn't. And you can kind of see like, hey, like this is how a vulnerability leaked into an ecosystem package, which meant that if you were using this ORM in your package, in your application, you had a SQL injection in production, which is not fun. So this was a quick one I wanted to go through. Supply chains are an interesting problem. NPM, apt-get, Ruby gems, pip, all of these ecosystems are built on a network of trust. We are trusting that the people who are building the modules that we're using are trustworthy, that we can use their code, and we can even go through and review the code and ensure that like what we're reviewing is, going to work. The event stream module was hacked in a way that was pretty ingenious to hack Bitcoin wallets. It was caught before it went out in production, I believe because of a programming error, because the person didn't understand how weird JavaScript is. But essentially, someone got the rights handed over to them to publish event stream. It was unclear 100% if the person who published the vulnerable version of event stream was aware of the vulnerability or if they themselves had been compromised. Keep your keys close. But essentially, what it was able to do was it had a payload and a test in a binary format. It would check on the system to see where it was in the depth of your package. So if you were in a Node application that was using a very specific package for a coin wallet, they knew that the coin wallet had event stream 2 depths down from it on the file system. So the key that this binary was encoded with was the path of a thing in the package JSON of the module that it expected to be in. So essentially, like when you ran npm install for that crypto module, if you had for that Bitcoin module, if you had that coin module in your path, it was guaranteed that you were going to have a hidden file on your system somewhere that would have the keys to your Bitcoin wallet. So basically, on install, it would grab the binary, it would try to decode it with the information it got from the package JSON 2 levels up. And if it decoded, the payload was the string that would exfiltrate that data from your system and then send it over the wire. And I believe it also was doing something where like it only did it if the Bitcoin wallet had more than like $20,000 in it or something like that. It's like regular day Robin Hood. But this is a great example of like a supply chain attack. Someone got access to being able to publish the module. They scripted an attack that would be almost unobservable. It was in the published package, but not in the tarball that was pushed to GitHub and not in the source code that was on GitHub. So you needed to get the tarball from NPM, extract the tarball from NPM, look at all the code, and the actual code that did the attack, for the most part, looked completely ambivalent because the actual payload was encoded and could only be decoded if it was inside of your dependency tree in exactly the right way that the attack would work. Yes, so the computers are bad. You can look this one up if you want to see more information about it. But I think like part of the reason why I like to bring this one up is supply chain attacks are not a new thing. I mean, they're literally named after supply chain, which was part of like an industrial process because they happened with like literal machines back in the day. Every single distributed ecosystem is vulnerable to these supply chain attacks. It can happen on GitHub, it can happen on pip, it can happen on Node. Node itself happens to have a very broad ecosystem, and packages tend to have a lot of dependencies, which make it more susceptible to these kind of attacks. But I would argue that it's arguably arrogant to pretend that Node is the only one who has to worry about these things. You have to worry about these in every single supply chain you're in. Further, you can do as much research and as much vetting as you want. Odds are you are probably going to miss that vulnerability that I just pointed out. You can't just solve this via looking at source code. Something that could have protected against this vulnerability is if you had network policy inside of the container of the runtime of the thing that you're running. So if you only ran npm install inside of a container and you locked down the network access of that container to only be able to hit like certain domains, well, then that attack never could have worked because it never could have actually broken out of the sandbox to get access to those other domains. Not trying to scare you into running Node only inside of a Docker container on your computer. I promise you, I don't have that much tinfoil on my head. But these are the kind of avenues that you want to think about, because you really can't solve every single problem. But what you can do is create process that will protect you. So how do you protect yourself? You know, like, one is to always use the latest version of Node. There's a tool called npm audit that can be used to make sure that your packages themselves are up to date. Tools like Greenkeeper or Dependabot, which was recently purchased by GitHub, can be used to help protect your packages themselves. And you can audit all your dependencies. But even beyond that, you know, sandboxing is something that you can think about as well. You know, and that sandboxing can help you maintain velocity. Because if you get too strict into the auditing side of things, you can hurt velocity, and then people just won't go through your audits. So, you know, where you run your code also plays a big thing in this. I don't think I left time for questions, did I?
You have a couple minutes.
Okay. So yeah, like, I talked for a bunch. I'll let you maybe talk a bit. Thanks for listening.
Thank you.
Thank you.
Did you like maybe one question?
Yeah. Anyone?
How many vulnerabilities come out of your team, like either to like in projects or like your dependencies where you discover something's wrong with the dependency because it got reported first to you guys, or because you guys just know your platform?
The team being like Node itself?
Yeah.
So thankfully right now with the way that HackerOne triage is set up, there's like this pre-triage that's run by HackerOne. So very rarely actually do the ecosystem vulnerabilities make it to us. They get caught by the HackerOne triage and triage to the third party first. But that's where there's actually been false positives, where things that should have been reported to core got reported to the ecosystem triage team. But we do find vulnerabilities in V8. We found like a handful of those vulnerabilities even in Node were found by like security researchers on our steering committee. But the Node project as a whole is not actively doing a lot of security research.
Cool. Thanks so much for
Well, thank you, everyone.
Really appreciate it.